Right.
Your problem was the opposite.
Derivative of velocity is acceleration.
So this is, so if you're given d, velocity is the derivative of the distance, acceleration is the derivative of the velocity.
If you're given d, so right, so time, distance, time, distance, velocity, acceleration.
Right.
And these are the derivatives down here.
Yes. Well,
Or how
this
do
is, here's my way of organizing.
how'd you denote that?
No offense. We're going to do a concrete example.
Because I think there's something that everyone who's good at calculus understands that a lot of beginners don't. Okay.
Is that okay?
Yes.
This is, height is distance.
Right.
What do you think height is being vertical distance?
Right.
So here is a rocket launcher.
Mm-hmm.
Okay?
Yes.
As it goes up, it's the rate at which it's going up is slowing down. It's getting smaller, which means its velocity is getting smaller until it hits maximum height.
Mm-hmm.
Then, so it's still going up. Then it hits so for the first whatever seconds, it's zooming up, but it's going slower and slower and slower and slower because gravity's pulling it down.
Mm-hmm.
At some instance of time, the velocity is 0. That's the maximum height.
Right.
Because then it's going at a negative velocity, it's going down. It'll keep going down until it hits the ground. In physics, the 10 is 10 feet. It was launched 10 feet above the ground. Okay? The time is in seconds.
Okay.
Its initial speed was 88 feet per second. It's like you shoot a gun, muzzle velocity, and as it goes up, it's slowing down. 80 feet per second, 60 miles an hour, by the way. Is that okay?
Yes.
So we could have something like this. This is height. This is time. This is height. It started at 10 feet. It's going straight up and straight down, but we're plotting height as opposed to time. So it's a parabola. Downward opening parabola. Is that okay?
Mm-hmm.
There's some instant where the time will be
Where the height will be.
maximum.
Right.
Now notice please, if I take the derivative of height is velocity. Velocity is positive. But what's happening, velocity is the slope of the tangent. It's getting smaller and smaller until at some instant in time, the velocity is 0. That's when the slope is 0. Then what happens to the slope? It's getting more and more negative. Is that okay?
Yes.
Now we could do time and velocity. If I take the derivative of height, that's going to be negative 32.2 t plus 88. Is that okay?
Mm-hmm.
That's velocity. Well, when time is 0, the velocity height. We'll be out of here. Professor came in and we'll be leaving. So at time is 0, the velocity is 88. And you know what it's doing? The velocity is decreasing. It's going slower and slower, still going up until it hits whatever this time is. Whatever that time is, it has a velocity of 0. It's hanging. And then what happens? The velocity turns negative. It's going down. So this point on the height corresponds to this point for velocity.
So they would really say that the velocity is negative?
Yes, because speed is just speed. Velocity is directed speed. Yes, velocity is direction. It's a vector. Now, if we do time versus acceleration, okay? The derivative of acceleration, of time, velocity, is acceleration. The derivative of velocity is acceleration. Please notice, this is a line. Its slope never changes. Its slope is, what was it? Negative 32.2 feet per second squared. There's your acceleration. It's a horizontal line because the acceleration is not changing. On your problem with Professor McLeod, the acceleration kept changing. So the acceleration itself was a line with a negative slope. It started here, and then when it hit there, the velocity was 0. Or, sorry, the acceleration change was 0. That's when the velocity was 180 miles an hour, or feet per second, 180 feet per second after 12 seconds. Then the velocity started going negative. I should say the acceleration was overwhelming the velocity, and it started slowing down.
Right.
But he said it didn't slow down. So for the first 10 seconds, 12 seconds, it was speeding up. For the first 12 seconds, it was speeding up. Then it leveled out at 180 feet per second.
Right.
This baby is always the velocity, the acceleration is always a constant due to gravity.
Right.
And so that line is the velocity line. Its slope, because it's a line, the slope of a line is everywhere the same. That's the acceleration. Now the problem becomes meaningless, or the formula becomes meaningless at the moment, at the instant the thing hits the ground. Because once it hits the ground, it's not going to go down anymore. So the velocity is suddenly 0, the acceleration is suddenly 0.
Right.
The time is whatever time that happened. And beyond that time, height is always 0.
Right. I think it's very useful to me to see this in conjunction with this.
Yeah.
Well, thank you very much.
Oh, you want to wish you were a better artist. February 14th, 1929. The answer is
St. Valentine's
the
Day
St.
Massacre.
Valentine's Day Massacre. Because February 14th is always St. Valentine's Day.
Right.
So then you guess it's the massacre.
You ever been down there?
No.
Clark Street?
I've been on Clark Street, but I've never.
I'm sure you've driven past it many
I'm
times.
sure.
It's just an empty lot now.
There's no building there anymore?
No.
I thought they preserved the wall with all the bullet holes.
I think they sold that off, as the story goes.
Did they sell by the hole or?
By the hole.